Rossa, and I work with the Research and Development Division of Inland Fisheries Ireland. And today, with my colleague Brian Coughlan, we're going to talk to you about fluvial biogeomorphic succession in channelized rivers, implications for river management. Okay, so this is our sample river, one of the rivers we're working on. This is a tributary of the Boyne River. It's called the Stonyford River, and it's in the east coast of Ireland. It's a lowland river with mixed bed load and quite a bit of fine sediment. Okay, so we were interested to see what would happen to the river if they stopped managing the river. And my slides are not in order, so I don't know. This one here. Slide is not here.
Hi, you totally fit.
Is missing.
Keep on that.
Okay, I'm missing a slide, so it doesn't really matter. But this is a channelized river. About a third of the river network in Ireland are channelized rivers, which is about 23,000 kilometers of channel. So it's a fair amount to channel, if you can imagine. Channelization is undertaken to increase water conveyance for the purpose of reducing flood risk and for land drainage. But what you end up with is quite poor habitat in terms of habitat diversity, because the hydraulics have been made uniform, sediment delivery has been changed, and the channel is very trapezoidal. So this river here, we asked them to stop managing the river in this fashion. So normally there's a dredging program that goes with the river to keep it in this state. And if you see up here on your left, in 2013, this was our river, and during when it was being frequently dredged. So they stopped dredging it and removing all the vegetation. You see it here in 2016, 2 years post dredging, and what we see is a lot of vegetation has established in the river. By 2017, the bottom left here, the channel is completely choked with vegetation. Now, normally they would come in and clean the river at that stage to improve water conveyance. However, we asked them to hold off, and by 2020, we see the river start to reassert itself, if you like. So we have stabilization of the river margins by vegetation, and we have development of a center flowing channel. And we see the pattern is going on as the channel evolves into 2021. So to try and explain what was going on here, we've considered it within this model. So the model is a biogeomorphic succession model. The model basically conceptualizes an idea of disturbance or destruction of landforms by flood disturbance, and the renewal and regeneration by engineered plant species. So this is a conceptual drawing of this succession model, and up in the top of your picture here, you see basically a plant form of the river. And in the bottom here, you see the cross section of the river. So this is the 4 phases of our biogeomorphic succession. So at point A here, we see where we have establishment of some aquatic plants in the channel. And in the cross section, you see they're below the water line. Given a bit of time, they start to trap sediment, and we get basically what we're calling a shelf here developing on the margins of the channel. It's starting to grade here, you can see in the cross section at the bottom. And given a bit more time, it grades further because it's trapping more sediment until it's up at the water surface. At this stage, we have a portion of the landform above the water surface, which allows other plants to come in and establish, those that aren't aquatic but might be wetland species. So they like wet ground, but they don't like to be inundated. And given more time, the landform grades even further. So we have basically an extension from the bank top down into the channel. And that allows terrestrial species or riparian species to establish at the top of the landform. In the model now, what would happen is basically we would have a flood disturbance or something, or so some of these phases from berm to riverbed could be reset. And what was typically happening in the channelized river is that with the dredging program, they were continuously coming in and resetting the river. So the river wasn't able to evolve and the landforms never evolved. Okay, so here's some pictures from our site showing some of these landforms and the sequence that takes place. So here we have the river about 3 years after they stopped dredging it, and we have a patch here, an embryonic patch of vegetation. Over time we get more vegetation, and that's trapping silt until we have a shelf developing, and that's probably at about the water, that's below the water surface. And give it a bit more time though, and we see what we have our benches here. So the actual sediment below that is up to the water surface. And given a bit more time on our left here, we see where it starts to terrestrialize, and these reed species are displaced by more kind of what we call terrestrial or riparian species. We see fairly considerable narrowing of the channel. So what we actually have here now is a two-stage channel, or a channel within a channel. So that channel there probably reflects the stream energy and over time rather than the engineered channel. Okay, so another feature of this was that we saw quite a change in substrate. So over time, we've been monitoring changes to hydraulics, to substrate, and to channel dimensions. And what we found is that after 2 years of the river being left alone, we started to get some pea gravel entering the river rather than just being covered in fine silt. And within 6 to 7 years, we started to see larger substrate. We surmise that that's basically down to the river being constricted, and we've got a much narrower channel with higher scour rates in the channel centre, and basically fine materials being scoured away. And for us, you know, in fisheries, that's really important because the bed is where fish spawn, and it's where also a lot of the insects that they feed on live in. And coarse gravel is a much better type of habitat. Okay, so just to say that these pattern or these landforms, we can call them pioneer landforms, they're not just happening in those rivers, obviously. So here we have up in the top left another lowland channelized river, but we have a bench development here, and here you see it in spring just as the vegetation is coming up. So it's just at the water surface level. Here we have our shelf, which sits below the water surface level. Down here in picture C, this river was previously straightened and the banks were riprap, so they've removed the riprap and they're just going to allow the river to migrate. And we got an island development here. Our pioneer vegetation starting to stabilize it. This may fill in over time, and we'll have our bank extension, and that of course has ramifications for the other bank because it might cause erosion on it and start a sequence of meandering, if you like. In D here we see an island development. This is a braided river during the summer, so that's why there's no water there, but you know, it's very flashy in the winter. And it's actually trees that establish these islands here because they're the ones that can withstand the erosional forces. And finally here in picture E, this is the River Liffey in Dublin, and what we see is full island development below a weir here. So by putting in the weir, they've obviously changed the hydraulics and sediment delivery in the river. So got zones here of very low shear stress, and these islands probably started out as little patches of aquatic plants, but now they're full-grown islands with mature trees growing on them. Okay, with that now, I'll pass you on to my colleague.
Hello there, my name's Brian Coughlan, and I'm going to show you some real-world examples of what we can do, you know, the constraints that we face, and how simple things can actually lead to quite sort of slow development of river habitat over time, which obviously leads into sort of resilience and resistance of that habitat. And, you know, basically more of our, the sort of like, as we're the fisheries, more of the species of interest to us in terms of trout and salmon. So in the real world, unfortunately, we work under these constraints. I mean, it would be wonderful to basically look at the river and say, okay, hands off, don't do anything more, let it go the way it wants to go. But unfortunately, we work in these constraints, and in a lot of cases in Ireland, there is legislative constraints. There's people who live in this modified landscape, and rivers themselves are highly modified. So we have to live where we live. So in terms of what we can do, here's a very simple diagram. It shows things as they change over time. This example is in the Camogue. It says down in the Meg, it's down in Limerick. And if we just go around slowly around the chart here, you look at the top here, we have topographic change. So that's a change in bars and in the shape and form of the channel. This channel, again, was significantly sort of modified during arterial drainage. As you can see, you can still see the trapezoidal shape in the bottom of the channel. So it's very simplified. Riparian completely removed, maintenance every 5 years, not much habitat in it. So what happened to us in this situation is that we got them to add quite a lot of gravel to the system upstream. And as you can see here, with the addition of the gravel then migrated downstream under natural sediment transport processes, and it forms this bar. That's the topographic change. You got riparian recruitment. As you can see, you have stuff just starting to recruit onto this bar here and at the toe of the bar. But that obviously, that'll change over time. It'll develop over time. And with that riparian recruitment, you'll have hydraulic change as the sediment is captured by these plants growing on the bar, as trees will start to grow up. And then as you have this happening, you'll have more sediment erosion and more sediment transport, and around we go. But the riparian vegetation and recruitment is very important because, you know, we have ecosystem change there. You have extra habitats created on the forming bar and on the bank face. And then we have thermal change later in terms of adding resilience to the system, in terms of modifying for climate change. You'll be like trees growing here that'll throw shade, drop woody debris into the channel, and then around we go. With the addition of woody debris, this cycle will continue. Another example here, this is on 20 years where the OPW stayed away. There was no river maintenance for over 20 years of works. So the only thing that's happened here was time. As you can see here, there's a big berm that's formed. It's completely vegetated. So that bar will obviously start as Rossa was saying, as probably underwater. Initial primary colonization by vegetation. That bar extended upwards, colonized by semi-aquatics, riparian. Now it's fully terrestrial. Obviously, then as that bar creates, it starts to erode on this far bank here. The water's flowing that way down the image, up the image. Riparian vegetation is going to recruit here. It'll have thermal change, shading, water temperature, and ecosystem change as this vegetation then affects the river. And around, you go through hydraulic change. Because this berm is pushing this way, it'll increase the flow. It'll start eroding on the right bank there if we look downstream. And it will have sediment erosion and deposition, which then will affect further downstream. And this pattern then continues. So in terms of this is very positive for us because you see that habitat will form from a very simplified channel. Processes are starting to occur. And then our final picture here. This is the White River in the Dee in Louth, which is under Dundalk. This is another arterially drained river. This hasn't been maintained in 30 years plus. So as you can see here, large woody debris in the channel, deep scour pockets, spawning gravels up here. Not huge amount of bank erosion, but lots of sediment transport. So you see that the in-stream bar, riparian recruitment, vegetation, lots of shading for maintaining water temperatures. You know, the ecosystem change, got all this wood and vegetational litter coming in, providing nutrients. The hydraulic change that's been created by, as you can see here, this big scour pocket, which has been created by this woody debris. With this woody debris is also capturing this, it's probably stabilizing this berm of sediment up here. As I said, erosion and deposition, more topographic change. And this is what is capable, the rivers are capable of doing if river maintenance isn't occurring regularly and the river can be just left alone. But unfortunately, this is not always the case. And as we went through these 3 slides, in terms of the stream biota, there's, to this final slide, it's probably more dynamic. There's probably more different types of species. There's probably greater biodiversity, and it's a big win-win, but it all in terms of, can it fit in the time and space of the landscape? Can you allow this to happen? So in terms of our implications for river management, you can see with 3 pictures here of OPW drain channels. This top left, it's been trapezoidally dug, maintained, livestock access, animals in and out. There is no riparian cover. There is no sort of in-stream development, natural progression. So in terms of, you know, it has very little biological capacity and resilience and resistance. In terms of, this is in center image is where the river is being maintained. They're taking out the material that's slowly forming a two-stage channel. And finally, another channel here where it's just been allowed run, you know, there's not been maintenance for probably 10 plus years, the narrow sinusoidal channel. So what we would be saying is that limited intervention, you know, really does promote recovery. And a fence in time, you know, does a lot. You don't have to be, you know, constantly modifying, creating management for yourself. That these rivers can heal themselves quite significantly.